Hello everyone, my name is Julian Kowalczyk and I will be going over problems 1 and 2 of homework 1 for the graduate class EL6303 Probability Theory and Stochastic Processes. So let's turn over to the answer sheet. So for problem 1, we were given the constraints. The probability of A has to be between 0 and 1, and the probability of B is between 0 and 1. Prove that the probability of A given not B plus the probability of not A given B is equal to 1 if and only if A and B are independent. So the definition of independence of A and B, one of the properties is the probability of A times B is equal to the probability of A times the probability of B. Given the equation, we can split up both the conditional probabilities using the multiplication rule into the probability of A given not B is equal to the probability of A times not B over the probability of B, not B, probability of not B. Make sure that's there. And then the other one, the probability of not A given B is equal to the probability of not A times B over the probability of B. Since this definition holds, the probability of A times not B is equal to the probability of A times the probability of not B. And I proved it here by showing that it expands to probability of A minus probability of A times B, and then you could factor out the probability of A because the complement is right here. Nope, not yet. It's probability of A minus A. You factor out the A, and then this is left with the complement, and that's where you get that. And vice versa with the other one, the probability of not A times B is actually equal to the probability of not A times the probability of B. So using these two substitutions into these two conditional probabilities expansions, we get the probability of A times not B over the probability of not B plus the probability of not A times B over the probability of B is actually equal to the probability of A times the probability of not B divided by the probability of not B plus the probability of not A times the probability of B divided by probability of B. So these two cancel out, and we are left with the probability of A plus the probability of not A, and that is equal to 1. So therefore, the whole equation 1 is equal to 1, and it is true. So when they are independent, this holds, and you're able to reduce it down to 1 and show that it is true. Now for the second problem, we were given a digital signal that is going to be so the digital signal 1 or 0 is transmitted through a noisy channel, and that the model I modeled this problem with a probability tree over here because of so many outcomes that we were given. So what I did to make it easier, event A is we transmit a 1. Event not A is we transmit a 0. Event B is we receive a 0, and event not B is we receive a 1. So from our starting point, we could either transmit 1 or transmit 0. And since we're going through this noisy channel, if we transmitted 1, we either receive 0 or receive 1. And vice versa down here, if we transmit 0, we either receive 0 or we receive a 1. Over here, I have mapped out depending on what happens, what the probability was given from the problem. So just a quick thing. In the problem it's stated there's a probability of 0.4 that we transmit a 1, and there's a probability of 0.6 that we transmit a 0. And based on the noisy channel, we had the probability that given we transmitted a 1, we were getting a 0 was 0.2. Given we transmitted a 1, we're getting a 1 is 0.8. Given we transmitted a 0, we got a 0 is 0.9. Given we transmitted a 0 and we received a 1 is 0.1. So the first part asks, what's the probability that 0 is received? So if we look, there's from our decision tree, there's 2 different spots where we would get a 0, right? Event B, we would receive a 0 up here and we receive a 0 here. Since it is based on the prior event and it's dependent, we times it. So right here you get, if we transmit a 1 and we get a 0, the probability is 0.08. If we transmit a 0 and we get a 0, the probability is 0.4. And these are disjunct, means they don't worry about each other. Then the overall probability that we're getting a 0 is, you add these two and it's 0.62. Now the second part asked us, what is the probability of error? So that means, looking up here in events, if we transmitted a 1 but we ended up getting a 0, or if we transmit a 0 and we end up getting a 1, so not be is receiving a 1. Yet again, based on the tree up here, right, you have to follow from the start. So we transmit a 1, but we receive a 0. This branch, the total probability is again 0.08 down here. The other side is if we transmitted a 0, but we received a 1, you again multiply these two, so 0.6 times 0.1, you get 0.06. The two outcomes are disjunct, so you add them, so the probability of error is 0.14. So that is all for problems 1 and 2. Thank you for listening.